Alright, for the introduction from our group, this project focused on manufacturing a 70-inch aluminum alloy wheel for passenger vehicle. So the wheel uses a six-spoke symmetrical design and is made from A356 aluminum alloy with T6 heat treatment. So compared to conventional steel wheel, aluminum alloy wheel are lighter, improve fuel efficiency, provide better heat dissipation, and have higher corrosion resistance. These properties make them widely used in the automotive industry. Right now for manufacturing issue, so manufacturing alloy wheel involves several challenges and gas porosity and inclusion during the casting and can reduce the wheel strength and fatigue life. Uneven solidification may also cause internal defects and dimensional disruption during the machining. High precision is required for critical features such as the center bore, wheel offset, and large hole. Therefore, a manufacturer must achieve high quality while maintaining efficient and cost-effective production. Alright, now for project goals. The main goal of the project is to develop a complete manufacturing process for producing a high quality 70-inch aluminum alloy wheel using the A356T alloy. The project includes selecting the appropriate material, designing the wheel according to automotive standard, uh, choosing the suitable manufacturing equipment, and developing a manufacturing process involving low pressure die casting. So T6 heat treatment, CNC machining, and CMM inspection. And finally, a bill of the material and manufacturing cost analysis are prepared to ensure both product quality are economic and feasibility.
Assalamualaikum. My name is Nur Aqil bin AIDY, matrix number MA24024. For the material selection, we have chosen A356 aluminium alloy to produce an automotive alloy wheels. A356 aluminium alloy is composed of 92.05% aluminium as the base element, together with 6.5 to 7.5% silicon and 0.25 to 0.45% magnesium. It has a tight control of impurities consisting of iron, copper, and titanium at less than 0.2%. A356 alloy are commonly undergo T6 heat treatment process that increases its mechanical properties such as increased tensile strength, yield strength, and elongation. Next is its characteristics. A356 aluminium alloy have a high castability characteristics. It possesses excellent fluidability and ductility. It is also resistant to corrosion as it has a natural oxide layer that creates a passivating effect when exposed to neutral condition. Its uniform microstructure provides good machinability and finishing. Its characteristic in good machinability and finishing are most favorable to anodizing, where it protects against corrosion, powder coating to give excellent color application, and also wear resistance, and excellent surface finish for aerodynamic application and aesthetics. The manufacturing equipment that will be used to produce automotive aluminium alloy wheels are first crucible furnace, which is a gas-fired pressure-sealed crucible melting unit equipped with automated argon gas degassing mixer. It can operate at steady temperature and it is able to remove dissolved hydrogen gases inside the material to prevent internal macroporosity. Next is the low-pressure die casting machine. It's specialized steel die assembly connected to a seal holding furnace through ceramic riser tube. It is integrated with automated water and air cooling pipes to control uniform crystal growth. Next, we will be using a T6 thermal solution and aging surface station. It is a dual stage, computer controlled heat treatment line that holds the part at a specific temperature for solution annealing. It is also equipped with integrated rapid submission water quenching tank, controlled at 80 degrees Celsius, and an artificial aging oven at 180 degrees Celsius. Next, we will be using a multi-axis CNC machining cell system. It is an automated high-precision workstation combined with a heavy-duty CNC turning lathe and integrated with milling spindle. It automates flash removal, facing, and also drilling holes. The final equipment that we will be using is a coordinate measuring machine, CMM. It is a 3D quality control machine equipped with highly sensitive mechanical touch trigger probe. It can provide the ability to evaluate three-dimensional coordinate profile. It can be used to compare with the original CAD design data with high accuracy and minimal tolerance. For the manufacturing process flow, it starts with melting and refining of A356 aluminium alloy. Raw A356 aluminium ingots are placed into the gas crucible furnace and heated past their melting point. Then, argon gas are pumped by an automated impeller through the molten aluminium. This process dissolves hydrogen gas and directly removes raw porosity. Next is the low pressure die casting process, where overpressure gas is fed into the furnace chamber and forces the metal up through the ceramic tube and into the die cavity. It can reduce oxide formation and minimize porosity. A computer-controlled cooling lines ensure a uniform and directional solidification pattern. The third process is T6 precipitation hardening. It is categorized into three sub-processes. The first one is solution annealing, where cast wheels are heated and kept for 9 to 10 hours and is air-cooled. This allows for precipitation hardening. The second step is quenching, where it is transferred into water bath kept at 60 to 80 degrees Celsius. This rapid cooling locks the dissolved alloying elements into a super saturated state at room temperature. The final step is artificial aging, where it is placed inside an aging oven at 180 degrees Celsius for 9 hours, reinforcing the magnesium 2 silicon cluster within the aluminium grain, thus significantly increase the wheel's yield strength and structural rigidity. The next process is high precision CNC automated machining. The automated CNC machining cell machine the parts to its final shape with tight dimensional tolerances. It can trim off excess flash metal, turn the inner and outer rim profiles, and machine the hub mounting surface to establish the correct wheel offset. It can also drill the center bore at low tolerance and cut the pitch circle diameter lug holes to match the vehicle's axle hub configuration. The final step is CMM and quality inspection, where we use a coordinate measuring machine, CMM, to confirm its geometric dimension. This physical dimension inspected using a three-dimensional coordinate system and will be cross-checked against the original CAD design model, ensuring the part satisfies structural tolerance.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Hafiz bin Abdullah. Thank you, Aqil. I will now present section 2.4 focusing on product design, build of material and economic validation of our wheel. As visualized here in our design model image, the wheel utilizes an engineered 6-spoke symmetrical layout. From a structural standpoint, this configuration balances maximum rigidity against dynamic cornering fatigues while minimizing rotational mass. Furthermore, this open geometry optimizes our surface area to volume ratio, significantly increasing convective thermal dissipation to quickly pull extreme heat away from the vehicle braking assembly and prevent brake fade. As for standard wheel nomenclature, the design target a 17-inch outer rim diameter, a 7.5-inch width, and standard 5 by 1 14.3mm lug pattern to ensure flawless integration with standard vehicle axle. To transition this design into a real-world factory production run, we established a structural bill of material optimized for a standard batch size of 1,000 finished units. This inventory configuration perfectly aligned with the processing stage discussed earlier. Our primary material matrix require 13,500 kg of premium A356.2 aluminium alloy ingots. To support the redefined step, we budget 120 kg of pure ultra-pure argon gas to completely eliminate hydrogen porosity during crucible melting. We accounted for 80,000 carbide insert to maintain our tight tolerance during multi-axis CNC machining, and 350 kg of polyethylene silver powder coat for ultimate environmental protection. This brings our total direct material asset cost to 182,202 ringgit. Finally, to evaluate if our production sequence is economically viable, we execute a detailed manufacturing costing analysis based on 4 industrial inputs: material, labor, energy, and factory overhead. While raw material makes up the bulk of the cost, our utility tracking captures the significant energy required to maintain the crucible melting furnace at 720 degrees Celsius and run the multi-stage T6 aging oven. By automating our line requiring only 5 skilled operators to supervise the LPDC and CNC lines, we successfully keep labor expense highly optimized. Summing this input yield a total manufacturing cost of 290,550 ringgit. Divided across our input volume, our final production cost sit at exactly 290 ringgit and 55 cents per individual alloy wheel. This cost is highly acceptable, commercially competitive, and thus demonstrates that our workflow perfectly balances structural safety with exceptional financial efficiency. Thank you.
Assalamualaikum. My name is Muhammad KHUARIZMI bin Muhammad KHAIRUL ANUAR, and my matrix number is MA24045. For my part, I will present the result and discussion section of our project on the advanced and sustainable manufacturing of automotive alloy wheels. This section focuses on 3 main areas. First is the cost analysis of producing the alloy wheels. Second is the energy usage analysis throughout the manufacturing process. And finally, I will discuss the sustainable manufacturing concept that can improve both environmental and economic performance. So, the analysis is based on the production of 1,000 units of 70-inch A356-T6 aluminium alloy wheels using the LPDC CNC manufacturing route. Firstly, let's take a look at the cost analysis. The total manufacturing cost for producing 1,000 alloy wheels is 219,550. This consists of 4 main components, which is material cost, labor cost, energy cost, and factory overhead cost. From the result, material cost contributes approximately 83% of the total manufacturing cost, making it the largest expense in production. This is mainly because a large amount of A356.2 aluminium alloy is required to manufacture the wheels. When divided by the production quantity, the manufacturing cost per wheel is 219 and 55. This result indicates that the LPDC CNC manufacturing process is economically feasible for medium to high volume production. Next is the energy usage analysis. The total energy consumption for the production process is approximately 35,200 kilowatt per hour. Among all the manufacturing stages, the melting and refining process consumes the highest amount of energy, accounting for 59.1% of total energy usage. This is followed by T6 heat treatment at 22.5%. LPDC casting contributes 10.2%, CNC machining 7.3%, and inspection and coating only 0.9%. These results clearly show that the thermal processing operations consume the majority of the factory's energy. Based on the energy analysis, melting and refining together with T6 heat treatment account for approximately 81.6% of total energy consumption. The main reason is that these processes require prolonged operation at high temperatures. For example, the aluminium must be heated to around 720 degrees Celsius before casting, while the T6 heat treatment involves solution heat treatment and artificial aging over several hours. Therefore, improving furnace efficiency and implementing heat recovery system can significantly reduce energy consumption. These improvements would lower operating costs and reduce the environmental impact of the manufacturing process. To improve sustainability, a closed-loop aluminium recycling system is proposed. During CNC machining, aluminium chips known as swarf are generated as excess material is removed from the wheel blank. Instead of disposing of this waste, the aluminium swarf can be collected and compressed through a briquetting process before being returned to the melting furnace. The recycled material can then be reused in the production of new alloy wheels. This approach provides several benefits, including reduced raw material consumption, lower purchasing costs for virgin aluminium, reduced waste sent to landfills, and significantly lower energy requirements compared to producing aluminium from raw ore. Besides recycling, thermal modeling and process optimization can further improve manufacturing efficiency. By using thermal simulation and finite element analysis, engineers can optimize the cooling channels inside the LPDC die. This helps achieve more uniform solidification, reduces casting defects such as porosity and shrinkage, improves mechanical properties, and lowers rejection rates. As a result, less material and energy are wasted during production. Overall, the combination of aluminium recycling and thermal optimization provides several benefits, including reduced carbon emissions, lower energy consumption, improved resource utilization, reduced production costs, and enhanced sustainability. That's all from me. Thank you.
Alright, in conclusion, this project successfully developed a complete manufacturing process for producing a 70-inch passenger alloy car wheel using the A356 T6 aluminum alloy. The selected material offer excellent strength, lightweight performance, corrosion resistant, and good casting and machining properties. The manufacturing sequence consisting of melting and refining, LPDC casting, T6 heat treatment, CNC machining, and CMM inspection was shown to be effective in the producing high-quality alloy wheel. So the cost analysis indicate a total production cost of 290,550 for 1,000 wheel, which is equivalent to RM 219.55 per wheel, with material costs contributing approximately 83% of the total cost. And finally, implementing recycling and process optimization improve sustainability by reducing waste, energy consumption, and the carbon emission. Therefore, the proposed manufacturing process is technically reliable, economic, feasible, and suitable for the large-scale automotive alloy wheel production. Thank you. That's all from our group.